Good morning. I welcome you all for the lecture series in mechanics of solids. And today we have a topic or a picture in the slide. Will you be able to identify what is this picture? Yes, it's a overhead tank. It's in the form of sphere and cylindrical form. So we will discuss what is the stress analysis in thin cylinders. This presentation covers stress analysis in thin cylinders. We will explore their applications and defining characteristics. Understanding stress distribution is vital for structural integrity. So the basic concepts of pressure and stress. Pressure is the force per unit area measured in PSI or kilopascal. We will consider three types of stresses, that is circumferential stress, longitudinal stress, and radial stress, where radial stress is negligible in thin cylinders. So first of all, we will discuss what is thin cylinders. When the thickness to diameter ratio is less than 1 by 20, it is called a thin cylinder. When it is greater than 1 by 20, it is called as thick cylinders. So in the thin cylinders, whenever the internal pressure is developed due to the fluid present inside the cylinder tends to fail in two ways. One is in the axial axis of the cylinder. The other one is perpendicular to the axis of the cylinder. The cylinder will get into split into two parts in both the ways, and the stress induced in the circumferential part we call it as hoop stress, and in the lengthwise we call it as longitudinal stress. So radial stress is also there, which is negligible. So circumferential stress, we have a formula of P into R divided by T. Here P is the internal pressure, R is the radius, and T is thickness. Let's calculate an example to demonstrate. Formula hoop stress sigma equal to PR by T. Using this formula, we can calculate the circumferential stress. And longitudinal stress, the formula is PR by 2T. This is related to circumferential stress. Let's calculate an example to demonstrate this stress. So the formula will be PR by 2T. P is the internal pressure of the fluid that is stored, and R is the radius of the cylinder, and T is the thickness. Stress state and principal stresses. Principal stresses in thin cylinders are sigma 1 equal to sigma theta and sigma 2 equal to sigma 1. The maximum shear stress is sigma minus sigma L, that is divided by 2, will give you PR by 4T. More circle visually represents the stress state. So we have different failure theories for the cylinders and spherical shells. The common failure modes include yielding failure, fracture failure, and buckling. Yield criteria like 1 misses and crucial are crucial. Safety factors are typically 2 to 4. We will look at the example to determine allowable stress. So yielding is nothing but extension of length, and fracture is nothing but breakage of fiber, and buckling is nothing but load that is combined due to compressive stress happening in the joint. And these are the three failure theories that is considered in thin cylinders. And we have applications and case studies. Application include pipeline, pressure vessel design. Also aerospace structures use lightweight cylinders. Pipelines, we used to calculate the wall thickness of the pipelines, and the pressure vessels as per the ASME code, and aerospace lightweight cylinders, we will calculate the circumferential stress and hoop stress and longitudinal stress. So the key takeaways and future directions: accurate pressure and dimensional measurements are key. Finite element analysis handle complex scenarios. Emerging research involves composite cylinders and non-destructive testing. So accurate data is very important to measure the stresses associated in the pressure vessels. And for complex cases, we need to adopt finite element analysis. And for composite cylinders, we need to do research to find out the pressures involved in the thin cylinders. Thank you all.